Hi, my name is Chelsea Carlson, and I'm a PhD student here at Queen's University in the Department of Physics, Engineering Physics, and Astronomy. My field of study is theoretical nanophotonics. Photonics is the study of light-matter interactions. Nano means the nanometer scale, which is the size scale of things like bacteria, viruses, and large molecules. And theoretical means that I don't work in a traditional lab. My lab is a high-powered computer where I write sophisticated codes and use interesting softwares to develop and explore existing and new theories in my field of study. Today, I'd like to talk to you about the electromagnetic spectrum, or the light spectrum. There are many properties to light, but one of the most important ones to me in my work is the wavelength of light, which is the distance between one peak and the next in the wave. Now, the visible spectrum, which is the spectrum of light that we can see with our eyes, and that includes all the colors from indigo to red, is actually only a very small sliver of this spectrum, and it ranges from about 400 nanometers to 700 nanometers. However, the spectrum, as you can see by this diagram, has wavelengths that range from the size of cities and buildings, which are radio waves, all the way down to gamma rays, which can be as small as, well, it can be much less than an atom in size. So this whole range offers different applications and different areas of physics, um, like microwaves, X-rays. Uh, but what I want to look at today is the visible spectrum. And specifically, I'm going to talk about two regimes of the spectrum. The first is the narrowband regime, and this is where we're talking about single wavelengths or a very small range of wavelengths. Applications that fall into the narrowband regime are things like lasers that only emit one wavelength of light at a time. In this laser here, we can see that it emits green, so it operates at around 600 nanometers. As an engineer, I want to know, well, how do I manipulate this light to do different things that I want it to do? One way to do this is using photonic crystals. A photonic crystal is a periodic pattern of material on the nanoscale, which can manipulate visible light. Interestingly, nature already does this. If you've ever looked at a butterfly and observed its beautiful colors, those colors arise from nanoscale periodic patterns in its wings. And depending on the size and type of pattern, you will see different colors. Another animal that benefits from photonic crystal patterning is the peacock. If you take a microscope and zoom in on one of its feathers, you'll see a periodic pattern, much like the butterfly wing. And depending on how this pattern changes, you will see different colors. In the laboratory, we can actually recreate these patterns and do interesting things like bend light at 90-degree angles. The second regime that I'm going to talk about is the broadband regime. And unlike the narrowband, this works at a range of wavelengths. The best example of broadband spectrum is the sun. The sun emits light not just at one wavelength like a laser, it emits light at pretty much all wavelengths, from the ultraviolet, or UV, down to the infrared, or IR. And this includes the visible spectrum that we know, or that we see, not that we know. And this is why when you buy things like sunscreen, they should say broadband or broad spectrum, because you need to protect your skin for a wide range of wavelengths from the sun. One way that we can manipulate light in the broadband spectrum is using things like metal nanoparticles, and this is what I do in my research. A metal nanoparticle is a metallic object, usually gold or silver, um, but it can be many other materials as well. And it's on the micro or nano scale, and it can manipulate visible light over a broadband range of wavelengths. One of the cool things about these metal nanoparticles is that depending on the shape and size, you can get them to operate at different wavelengths. So for example, this picture in the bottom corner is from a paper I wrote on bow tie nanoantennas. And what a bow tie nanoantenna is two metal nanoparticles, in this case made of gold, and when you bring them together, you can actually form a hotspot where the light is, you can call it trapped. And when it's trapped, it interacts with the matter around it at a higher rate. However, metal nanoparticles are not a new thing at all. We've actually been using them for thousands of years in things like stained glass. Since we can easily tune the color that is emitted from these particles, based on the size of the particle. Stained glass makers have been using these for millennia to create the different colors in stained glass. So I hope you found this interesting, learning about the difference between narrowband and broadband electromagnetic spectrums. And I hope you enjoy the rest of Science Rendezvous. Thank you for joining me. Bye.